Hello, my name is Andrea. I'm mainly going to be teaching AP Physics C, E&M and Mechanics, AP Physics 1 and 2, and AP Biology. I have about 3 years of assorted tutoring experience. A majority of this began in my high school's Math and Science Tutoring Center, where I taught everything from general to honors to AP, biology, chemistry, physics, and math, ranging through AP Physics C and AP Calculus BC. I also served as a leader of this tutoring center for 1 year, coming up with better tutoring strategies, helping match tutors and students, and designing math and science outreach events. In addition to this, I served in my high school's Humanities and Writing Center for 1 year, coaching English and history. I've served as a debate coach and public speaking coach, and actually worked for 1 month as a full-time debate and philosophy teacher. I also have some experience working part-time as a private tutor for math and physics. Over this time, I've really grown to love tutoring because it gives me a chance to show my students what's so beautiful about the concepts that they're learning in class. I like giving students a kind of scaffold of core principles that they can build up upon to come up with problem-solving strategies that will help them on their homework, help them on their tests, help them on AP exams, so that they can really build an intuition for what they're learning. Okay, today I'm going to be talking about one of my personal favorite electromagnetic concepts and something that really lies at the heart of electromagnetism, which is Gauss's law, this equation integral of E dot dA equals Q enclosed over epsilon naught. If this notation looks confusing or unfamiliar, don't worry because I'm going to break everything down and explain how it works. But first, I want to explain why Gauss's law is useful in the first place and what it does. Gauss's law is useful in situations where we need to calculate the electric field generated by some unchanging charge distribution. Now, if you've done any E&M before, you probably already know an equation that tells you how to do this, something called Coulomb's law. This tells us that E is equal to kq over r squared, where k is this constant 1 over 4 pi epsilon naught. Coulomb's law is really great if you have something like a point charge and you want to find the field generated by it. You maybe have also used Coulomb's law to find the force between 2-point charges, something like a dipole pictured here. But what about a more complex charge distribution? What if you have something like a spherical conducting shell with charge distributed on the outer surface, or a solid conductor with charge distributed on the outer surface? Maybe you know how to use Coulomb's law for this, but maybe you don't. And what if you have something even worse, like a spherical conductor inside of a spherical shell? Gauss's law gives you the equipment to deal with all of this and actually even more complicated charge distributions, something like this, an infinite plane of conducting charge. Gauss's law gives you a really good intuition that helps you understand how the electric field is generated and what its geometry is going to look like. I just want to quickly, before I delve into more on Gauss's law, explain the situations in E&M, especially in AP Physics C, where you want to employ Gauss's law. And those are ones with familiar geometries, if you can call an infinitely charged plane familiar. Why this emphasis on geometry? That's because most Gauss's law problems really just come down to calculating surface area. Now you might be saying, Andrea, you're completely crazy. What's the link between surface area and electric fields? Now the two are connected by this concept called electric flux. This we denote with a Greek letter phi and the subscript e. And it's equal to these two things that make up Gauss's law, the surface integral of E dot dA and Q enclosed over epsilon naught. First, we're going to deal with this integral term. What does this mean? This basically tells us that flux is equal to how much electric field is flowing through a tiny element of surface area, which we call dA. Here's a graphic that might help explain that. The entire surface area of this sphere would be something called A. But as physicists and mathematicians, we don't like to deal with the entirety of something at once. We like to break it down into tiny infinitesimal pieces called differentials. And that's what this dA is. But notice that dA is not just the area of this differential, but it actually has a vector component, a direction to it. dA points perpendicular to the surface, not parallel. This is especially useful to us as we try to simplify Gauss's law, and you'll see that later. But first, I just want to show you a visual of what this integral expression tells us about electric flux. Here I have a zoomed in picture of this patch dA, and you can see the electric field generated by some charge distribution flowing through it. The number of field lines flowing through this patch dA is the amount of flux through this little patch. The integral over the entire area of all of these dAs, so the sum of all of those brought together, would be the electric flux through that entire sphere. Another thing to notice is that the electric field lines here are also perpendicular to the surface, pointing in the exact same direction as this area vector. This may seem obscure, but I promise you'll see how this simplifies everything in just a moment. Now let's look at the second interpretation of electric flux, the idea that flux is related to the enclosed charge inside of this surface. Intuitively, this makes sense. The amount of field flowing through a surface should be related to the amount of field-producing stuff or charge inside of the surface. What Gauss's law does is it takes these two concepts and uses the fact that they're equal to help us have a more intuitive way of calculating electric fields. Basically, instead of just calculating the potentially complicated electric field from a confusing charge distribution, we join it in with this almost crutch of a surface area by making an imaginary Gaussian surface, one that we know how to find the surface area of, and thinking about what the flux through it would be. This might seem confusing, but I'll put together a simple example that will help everything make sense in just a moment. But first, I want to deal with some of this scary-looking notation. There are actually a lot of ways we can simplify Gauss's law to the level that you really need it in AP Physics C that will help make it a little bit more intuitive. First, I want to deal with this dot product. E dot dA. A dot product is a type of vector product that basically means multiplying the magnitudes of the two vectors, E times dA, times the cosine of the angle between them, which we call theta. Now, in AP Physics C, there's really only two situations, two types of thetas that you're going to be dealing with. The first situation is when your electric field is parallel to the area vector. These are those examples I pointed out previously. In this case, theta is equal to 0. Cosine of theta is equal to 1, so the integral of E dot dA is actually just equal to the integral of E times dA, traditional multiplication. The second example is even simpler. This is the case where E is perpendicular to dA. That is, you have a field that's flowing along your surface. In this case, theta is 90 degrees, cosine of theta is 0, and your integral is even simpler because everything just goes to 0. I also want to deal with this integral itself. Like I said earlier, mathematicians and physicists like to deal with complicated things by breaking them into tiny pieces and building them back up. But a lot of the cases where you'll be using Gauss's law get rid of this whole complicated element and just use a solid that you know how to find the surface area of, something like a sphere or a cylinder. So we don't actually need to break it down, we can just deal with it as a whole. So instead of this integral of E times dA, you actually just have E times A, where E is some unknown electric field, usually, and A is some surface area that you know because you chose the surface to make things easy for yourself. In that case, we now have a much simpler looking Gauss's law. E times A equals Q enclosed over epsilon naught. Now let's deal with a simple practice example that will help explain and make light of why we deal with this whole imaginary solid Gauss's law problem in the first place. So this example I want to talk about is the one I introduced at the beginning of this explanation, a conducting solid with a charge distributed on the outer surface. Notice that this solid is spherically shaped, although my drawing isn't perfect, and has a radius of A. The way that any Gauss's law problem is going to start is with you designing some Gaussian solid, some invisible imaginary surface area that you're going to put around this charge distribution. In this case, we choose a sphere with a radius R. It's totally imaginary. You're not actually implementing this, but it's a tool that you can use to think about things. Why? Well, I want to bring back to some of that area electric field vector pointing stuff. If you can see in this visual here, all of the area vectors of this sphere are pointing in the exact same direction as the electric field vectors generated by this charge distribution. That means that this simplification I just introduced, E times A equals Q enclosed over epsilon naught, works, and we actually have a really simple problem to solve. With this in mind, let's take a look at the unknowns and the knowns of this problem. What do we know? In any Gauss's law problem, there are going to be three unknowns, E, A, and Q enclosed. In this case, E is still unknown for now. A, though, we know. That's just the surface area of a sphere. Your geometry teacher probably taught you this, and you probably forgot it, but by the end of Physics C, you will remember it again, I promise. 4 pi r squared. Q enclosed, also we know. No matter how the charge is distributed when you're really close to this solid, when you're on the surface of this imaginary Gaussian sphere far away from it, you can see that the whole bundle of this charge is just carrying a total of plus Q. Okay, now we know what all of our variables are equal to, so we can plug everything back into the simplified Gauss's law. And now we get 4 pi r squared E equals plus Q over epsilon naught. Rearranging to solve for E, we get this expression E equals plus Q over 4 pi epsilon naught r squared. What's really exciting about this is it's exactly the same as the equation introduced at the beginning of this explanation, Coulomb's law for a point charge of magnitude plus q. And actually, when you're at a radius that's far away from a complicated charge distribution like this, where r is much greater than a, you see that this whole distribution actually just collapses down into a point charge of magnitude plus q, a really beautiful and elegant concept. So I hope you understand now a little bit more of where Coulomb's law comes from. And I also hope you're not sitting there saying, well, we could have just used Coulomb's law for all of this. Gauss's law is an incredibly powerful tool that gives us the intuition, yes, to deal with point charges or spherical charge distributions, but also allows us to ask questions about what's inside of this sphere, or if we put the sphere inside of something else. Okay, so that's my explanation of Gauss's law. I hope you enjoyed the explanation and you learned something. I know I always love talking about Gauss's law. I'm excited to teach you more physics if you're interested, and I look forward to hearing from you soon. Thank you, bye.